Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the built-in voltage in PN junctions. Let's start. By the time you finish this lesson, you will learn the electric field waveform in the depletion region, built-in voltage, type of the PN junction, temperature effect on the built-in voltage, and the energy band diagram of the PN junction. In the previous lecture, I explained the formation of the PN junction and the diffusion and drift currents. In this lecture, you are about to learn the built-in voltage, a product of the electric field formed in the depletion region. We already know that a PN junction in the equilibrium has three regions, two neutral regions and one depletion region. In the depletion region, there is an electric field directed from the N semiconductor to the P semiconductor. If I draw the x-axis alongside the PN junction, I can label the boundaries of the depletion region by xp and xn. In the space between xp and xn, there is an electric field, but how does it look like? If I draw the electric field strength versus the x-axis, I find that the electric field at xp and xn is 0 and it linearly increases by moving toward the junction center. At the center of the depletion region, the electric field peaks. Now, imagine that I have a unit charge and I put it right at xp. This unit charge is positive and has a charge of 1 coulomb. How much work do you think is required to move this unit charge against the electric field in the depletion region from xp to xn without causing any acceleration? If you think enough about it, you'll realize that if you were able to calculate this work done per unit charge, you could calculate the voltage across the depletion region. This voltage is called the built-in voltage, and in this course, we show it by V sub Pi. The built-in voltage is sometimes referred to as the forward voltage, barrier voltage, or diffusion voltage. It turns out that the relationship between the voltage and a static electric field is already formulated. As a result, we can calculate the built-in voltage by integrating the electric field from xp to xn multiplied in a negative sign. So, if you do the calculation, the waveform of the voltage across the depletion region is obtained. The amplitude of this voltage is the built-in voltage. In general, we have two types of PN junctions. The first one is the abrupt PN junction. In this course, I mostly focus on the abrupt PN junction. This gives us a framework to learn the most important concepts related to the PN junction. In the abrupt PN junction, the majority charge carriers are abruptly changed from N to P or from P to N at the junction. The majority charge carrier concentration versus the x-axis in the abrupt PN junction looks like this. The second type of PN junction is gradient PN junction. In the gradient PN junction, the transition between P and N happens at a low gradient. The majority charge carrier concentration versus the x-axis in the gradient PN junction is shown here. What we should pay attention to is that the whole semiconductor is doped by donor dopants with the concentration of Nd. Later in the manufacturing process, the acceptor dopants are diffused from the left side. This is why when we get closer to the junction, the concentration of acceptor dopants Na gradually degrades and finally fades away. For an abrupt PN junction, if I assume that all of the dopants are ionized, the built-in voltage can be calculated by this equation. As you can see, the built-in voltage depends on the temperature and the concentration of dopants. Let's draw the built-in voltage versus the dopant concentration at 300 degrees Kelvin. As you can see, the built-in voltage is proportional to the dopant concentration. As a result, increased dopant concentration increases the built-in voltage. By looking at the VBI expression, we can also see that VBI is proportional to temperature. Now, let me ask you a question. What will happen if I increase the temperature to 400 degrees Kelvin? Will I get a higher VBI or a lower? Think about it for a few seconds. You may also want to stop the video while you are thinking about it. Here is the VBI ND diagram at 400 degrees Kelvin. You see that VBI is reduced by the temperature increase. But hold on a second, how come this happened? The answer is that VBI also depends on the intrinsic charge carriers. In previous lectures, we calculated Ni. Ni is obtained by this expression. Increased temperature increases the intrinsic charge carriers. Since Ni is the dominator inside the natural logarithm expression, its effect is more profound than the temperature coefficient. This is why VBI decreases by increased temperature. As you remember, in one of the previous lectures, I was discussing the side-by-side energy band diagrams of the P and N type semiconductors. I have them drawn here one more time. What I did not talk about was the shape of the energy band diagram in the depletion region. It's now time to discuss it. In the depletion region, the energy levels EC, EB, and EI bend. However, EF remains intact. In equilibrium, the Fermi level EF is a constant and therefore can be taken as a reference energy to draw other energy levels. In this lecture, I discussed the electric field in the depletion region, built-in voltage, types of the PN junction, temperature effect on the built-in voltage, and the energy band diagram of the PN junction. In the next lecture, I will discuss the current flow mechanism of a PN junction under forward biasing. Thanks for joining this lecture of Peacademia.